All right. Um, so today, I'll talk about something um, that you may encounter later on in many cases when you try to analyze electric current in a material, and that's about the position of Fermi energy levels. So, um, today we're going to talk about a special case like um, graded doping in semiconductor. Now, you might remember that when we talked about doping, let's say we have a material with a valence and conduction band, and we say typically we can take the middle as the Fermi energy. Although in reality, Fermi energy is not exactly at the middle. It depends on the effective mass of electrons and holes. Now, um, if I apply some doping, let's say I apply some N-type doping. So for instance, um, this is intrinsic material. And if I try to dope it with N-type material, then this is my EC conduction band, this is my valence band. And if you make N-type doping, that means you add more electrons. That can conduct current. Then EF, the Fermi level, that will go up. Okay. So the more you dope, the higher the value of EF will be, the closer it will be to the conduction band. So now, since I have two levels, I will call one as EF and the other one as EFI. EFI stands for intrinsic Fermi level. So intrinsic means when you do not dope anything, your Fermi level stays at the center. Once you start to dope it with N-type material, EF will go up. If you try to dope it with P-type material, EF will go down as close as possible to EV. Okay? So this is what we knew so far. And to remind you that how this EF and electron concentration is related. So electron or carrier concentration or electron density can be found by multiplying the effective density of states with the Fermi function. EC minus F by T. And we have to add a minus sign here. Okay. So from here you can see if EF is very close to EC, then this exponential term becomes 1 unity. That's the maximum value of exponential. Okay, so in that case, n is just equal to nc, which means whatever states you have, all the states are filled. And if EF is far away from EC, then this whole guy becomes very large. If this becomes very large, then exponential of minus infinity or minus a large value is very small. In that case, n becomes very small. Electron concentration becomes very small. Now, today we will see what if, instead of doping everywhere uniformly, what if we dope each different layers differently? Let's say we have a part of the silicon where we dope it very heavily. So EF is very close to EC. So this is my EF. This is EC. This is EFI. EFI stands for the intrinsic Fermi level, and EV. But then we dope the next part of silicon with relatively low doping. So this is my EFI. Because I dope it low, my EF would be little lower compared to the previous one. So maybe this is my new EF. And this is EC, EV. And then the third part, I dope it even lower. Okay. So if I dope it even lower, then EF is going to be as close as possible to EFI. So it is almost intrinsic. Okay. So I'll write it. High dope region, maybe mid-level doping, and very low level doping. Okay, so these are the three different regions. We have taken a silicon material, and in that silicon material, we have doped three regions in three different ways. We have doped this guy very heavily. Okay, this is high doping. And then this other part is mid doping. And the last guy is low doping. Okay, so three different kind of doping. And consider that these dopings are done not in a abrupt manner, but in a graded manner. Like we make a very heavy doping, but then we gradually decrease the amount of doping as we go to the other side of the material. So if that is something what we do, how the band diagram would look like. This is what we'll see today. So this is the individual band diagram, right? This is region 1, and let's say this is region 1, region 2, and region 3. For region 1, I have this, region 2, I have this, and region 3, I have this. So look at that. At region 1, because of heavy doping, EF is very close to EC. At region 2, EF is somewhat away from EC. And at region 3, EF is actually mostly close to EFI. But now, what is the final band diagram? Do you think a band diagram would look like this? Maybe you may guess that maybe the band diagram would look like this. We have EC here, we have EV here, and maybe EFI is all here. And how do you write, or how do you draw EF? You may guess that maybe I'm going to draw EF like this, and this, and then this, like a stair, right? Maybe if I were asked to guess, I would have guessed like that EF would look like a staircase because it has three different regions. And if I have continuous grading, like not an abrupt staircase, but a continuous grading, then maybe I would guess that EF would look like this. Instead of having a tape-like fashion, EF would continuously go closer to EFI as you go from left to right. That would be my initial guess of band diagram or graded doping. Okay. Now, is it correct? There is a problem in this diagram, and the problem is the following. The Fermi level basically, if you compare to Fermi level, that basically tells you whether an electron go from left side to right side or the other way. For instance, in the first case, you can see the Fermi level at the left is high and the Fermi level at the right is below, right? So for this case, electron must go from left to right. Like if you keep an electron here, electron must go and flow to the other way. Okay? So please remember that electron must flow from high Fermi level EF towards low Fermi level, low EF. And if this is true, then we do not have an equilibrium condition. You know, equilibrium means there is no more flow of electrons. Okay, so think about it. If you take a material and you just dope it, you dope some part very high and you dope some part very low, and then you wait. You of course do not expect that because of this different doping, you will have continuous flow of electrons, right? Because there is no battery, right? Without battery, you cannot have continuous flow. So initially there will be a flow, like for maybe a fraction of a second, I don't know, maybe for a nanosecond, there might be a flow of electrons, but then very quickly it comes to a stable state. So in the stable state, if since there is no flow of electrons, so that means in the stable condition, EF must be same all through the material. Okay, so I'll write the second part, which is also very important. That at steady state, Fermi level must be same all through the material. Okay, so when you initially dope the material, for the first few split of seconds, you may have some redistributions of carriers from one part of the material to another part, but then very quickly it comes to a stable state and there will be no more flow of electrons. So in that stable state or steady state, so at steady state, the band diagram would look like this. I know from this rule that at steady state Fermi level must be same. Okay, so instead of first drawing EC and EV, first I'm going to draw EF. Okay, and I know that EF is going to be constant. So I'm going to draw EF first. And then by keeping EF at this level, I'm going to redraw this EC and EV. So how I'm going to draw this? Look at that. At the region, like region 1, where you have very heavy doping, I know that my EF must be very close to EC, correct? So if I keep EF fixed here, I'm going to draw EC actually here. Okay, so this is my EC. But then in the second region, I know that EC and EF, they will depart from each other. Okay, so at the second region, maybe I will draw EC like this. And at the third region, EF and EC, they are actually farthest from each other. So at the third region, maybe I will write EC like this. Okay, so if it is a graded doping, then I can draw a continuous EC which will go from low to high like this. Okay. And also, how about EV? Let us try to draw that. EV, look at that. At the first region, EV and EF, they are farthest from each other, right? So I'm going to draw EV farthest from EF. And by the way, remember that EV must be away from EC by the amount of band gap. So the band gap is EG. So that's why when you draw EC, and for a given material, you can easily draw EV because you know that for what material, what is the corresponding band gap. So EC and EV must stay away from each other by an amount of EG. So if EC, it goes from left to right like that, it must be true that EV also go from left to right like that. Okay, making sure that always they are EC and EV are apart from each other by the band gap EG. So how about the EFI? EFI, remember, EFI is the intrinsic Fermi level. So intrinsic means when you do not dope anything. And if you just take the midpoint, then maybe the midpoint will also go like this. So this is EFI, EFI. Okay. So one more time, EC, we first start by drawing EF because I know that at steady state, there must not be any flow of electron. That means EF must be constant. And I draw a constant line of EF. And then with respect to EF, I draw EC. I draw it in a linear manner. It goes from left to right. And as it goes right, the distance between EC and EF increases. Because I know that I graded very heavily doped, and I doped very lightly on the other side. That's why EC and EV would look like this. Okay. Now, if EC and EV are bended from left to right, that would create an electric field. Okay. So when we talk about the electric field, remember that an electric the like a battery. The job of a battery is to create a potential difference between one side and the other side of a wire. So if I have an electric field that goes like this from left to right, it will create an electric field and it will try to take a electron. Let's say if an electron is here, then because of this electric field, an electron will try to move downward. Okay, so always remember that whenever you see a curvature of EC, this means that this slope will create a pull for an electron. So electron will always try to go low. Okay, always try to minimize its energy. Yes, yes. So you see there is a in one case I said that at the steady state EF is constant, right? On the other hand, I say that if EF has to be constant, and we also need to make sure that it is graded doping, that means EC and EF will change their distance as you go from left to right. That means EC must have to bend upward, right? But if EC bends upward, it will pull an electron which stays on the right side. Okay? It will create a pull. So these are the electric field. So now there is another problem, right? Because I say that it's a steady state. So at steady state, no electron can move. Okay. So there must be something at this picture which will balance, which will counterbalance the pull of these electrons by something else. So what is that counter force that will keep electrons to flow from right to left, to prevent electrons from going from right to left? And that pull actually comes from the diffusion pressure. So remember in the previous class we talked about diffusion, like if you create um, heavy concentration of particle in one region and low concentration of particle in another region, then the particle will try to flow from heavy concentration to light concentration, okay? And it will keep flowing unless the concentration becomes equal, uniform all over the place. So let us see how diffusion actually helps us to achieve steady state. You see, the problem here is that at this state, we cannot really set a steady state because it is bent and electron must come from right to left. So what is missing here from this picture is that diffusion part. So in the left side, I know that we doped it very heavily, so we must have a lot of electrons, right? We must have a lot of electrons in the left side, correct? But as we go from left to right, we must have less and less electron, isn't it? Because we doped it gradedly, right? We doped very heavy in the right side, but we in the left side, but we doped gradually low as we go towards the right. So electrons must have less and less concentration. So I'm going to draw a lot of balls or bubbles just to represent electrons. But then as I go to the right, I'm going to draw less and less number of dots. The dot represents the electron. And now you can see that there is two different pressure on electron. On one side, electron must have a pull from right to left like this because EC is bended, right? On the other hand, because there is a lot of electrons on the left side and very low amount of electron on the right side, there would be another pressure that will push electron from left to right. Do you see this? So these two forces at the steady state, these two forces will counterbalance each other. Okay, so this is why electron will stop flowing. So I'm going to write it here that at steady state, because of concentration gradient of electron, there will be a diffusion current from left to right. Okay, and we can write the formula of this diffusion current by following the rules that diffusion current must be a product of diffusion constant and the concentration gradient dn dx. Okay, so this is x, your x direction, and as you go towards right, your dn reduces, correct? So J diffusion is a product of electric charge, diffusion constant, and the concentration gradient of electron. And because of bending of the conduction band EC, there will be drift current from right to left, okay, the other direction. And you can write J drift is equal to the number concentration of electron, the velocity of electron, and the charge of electron. And the concentration of electron, the velocity of electron can be written as the mobility multiplied by the electric field multiplied by the charge of electron. And how to know what is the electric field? The electric field can be easily found by looking into the bending of dEFI by dx. Look at that. What is dEFI? dEFI is the intrinsic Fermi level. Now you can see that the way EC bends, the way EV bends is the same way that EFI bends. They all bends like the same way. So if you take the differentiation of any one of them, you will get the electric field. Okay, so this part tells you the electric field. Okay, so one more time, because of the bending of EC, I'm going to wrap up in just 1 second. So because of the bending of EC and EV and EFI, we must have an electric field, and because of the electric field, we will encourage the electrons to go from right to left. Okay, but because remember that this bending of EC and EV is done by graded doping. We made heavy doping on the left side and low doping on the right side. So because of this uneven doping, there is a very heavy concentration of electron on the left side and very low concentration on the right side. So this means that electrons must be encouraged to go from left to right. And because of these two different opposing effect, eventually electron will come to a stop. Okay, so when you start to dope it heavily and graded it as you go from left to right, there will be initial redistribution of charges, right? Electron will start to flow, but very quickly they comes to a steady state. And when they come to a steady state because of these two different interactions, okay, two different kind of forces. Okay, so let's just wrap our discussion for today just by writing one more line that at steady state, J drift plus J diffusion must be zero. Okay, this means it doesn't mean that each of them is zero. It just means that they are opposite to each other. Okay, so J drift is equal to minus of J diffusion, and that's why their total result is zero. So that means there is no flow of electrons. But this is the underlying interesting part here, that there are actually two different forces if you gradually dope a material. Okay, thank you so much. So let us, oh man.